So let's solve Cambridge International AS and A Levels Chemistry, Paper 1, Multiple Choice, October-November 2025, Paper 12. What is the electrons in boxes with the notation of Fe3 plus ion? So basically, first we have to figure out the electronic configuration of an Fe atom, and then we have to make an ion, and then we have to figure out the electronic configuration for the ion. So for that, we're going to need the periodic table. Where is Fe? This is Fe. Fe basically has 26 electrons in total. And if we try to do the electronic configuration of Fe, you realize that this is 1, 2, 3, 1, 2, 3, then this is 4, right? And this is the S block. This one right here is the D block. This one right here is the P block. So you have 3 blocks in the periodic table, S, D, and P. So what basically happens is that the elements that are in D block, like Fe, their last electron is going to be in the D subshell, right? So over here, for the Fe, the electronic configuration comes out to be 4s2 and 3d1, 2, 3, 4, 5, and 6. So it's 4s2 and 3d6. Okay? Because over here, for the D block, over here there's a 3, over here there's a 4, over there's a 5, so it goes on like this. So this one basically is 3d5 and 3d6, and this one's 4s2. That's how the electronic configurations work out. So for Fe3 plus ion, the first thing that I'm going to do is I'm going to tell myself the last shell electronic configuration, which was 4s2 and 3d6, right? But now when I talk about the energy levels, this is of an Fe atom and I have to draw for an Fe ion. Now if I tell myself about the energy levels, I know that 4s orbital, subshell orbital, whatever, okay, it has more energy, right? It has a greater energy once filled. Initially, it's on a low energy. That's why it gets filled first before the 3D. But once filled, it moves to a higher energy like this. So now it has more energy than the 3D subshell. So when we have to take out electrons, we're going to take out electrons first from the 4s and then we're going to take out from the 3d. So 4s has more energy, so we're going to take out electrons from the 4s first. So we have to take out 3 electrons because it's 3 plus. So the first 2 electrons we're going to remove from 4s and then 1 electron from the 3d. So I have to remove 1 electron from 3d, so it's going to become 3d5, right? So if I check for the electronic configuration, it's 4s and 3d5. 4s means that there's no electron in the 4s. So this one and this one in 3d5, 1, 2, 3, 4, 5, which makes option D the correct answer. Okay. Which equation has the energy change that is equal to the first ionization energy of bromine? Okay. First ionization energy of bromine means that we have to take a bromine atom which is in gaseous state, and then we have to pluck out 1 electron from it, 1 electron. And when we're going to take out 1 electron from a neutral atom, it's going to form a positive 1 ion, which is going to be a gaseous ion, plus the 1 electron that we have taken out, right? So let's see which equation represents this. Not a negative one. We are taking out an electron. So when we take out electrons, something gets a positive charge. So option A shows exactly this equation, right? Next, the reaction of hydrogen sulfide with sulfur dioxide gives sulfur as one of the products. So we have hydrogen sulfide. We're making it react with sulfur dioxide, and we get sulfur, 2 moles of hydrogen plus 2 electrons, and then we have sulfur dioxide plus 4H plus 4 electrons. We're forming sulfur plus 2 waters. How many moles of hydrogen sulfide are needed to react with sulfur dioxide to produce 1 mole of sulfur? So the first things first, you can see that two half equations are given. Okay, one is the equation for the uh, loss of electrons. Two electrons are being lost, and this equation is for the gain of electrons. So the upper equation shows the loss of electrons, which is known as oxidation in chemistry, and the lower equation shows the gain of electrons. Four electrons are being gained. So this shows the reduction. Now, what do we have to do? We got to make sure that the loss of electrons and the gain of electrons are always equal. So we know over here 4 electrons are being gained. So 4 have to be lost as well. So first things first, we got to multiply this equation by 2. Okay, so at least we have a balanced equation. When we multiply this equation by 2, we get 2H2S, 2 sulfurs, 4 hydrogens, and 4 electrons. Now the loss and gain of electrons is equal on both sides. So now we can combine the two equations. How do we combine the two equations? We write all the things that are on the left side like this on the left side, and all the things that are on the right side on the right side. So over here I'm going to form my new equation. Not my new equation, it's just going to be the similar one, but I'm going to combine. So I have 2H2S plus 1 sulfur dioxide plus 4H plus 4 electrons. I'm going to cancel out the things that come on both sides later on, and then it's a reversible reaction. And now I have to write the products of the upper equation. 2 sulfurs plus 4H plus 4 electrons. Now the products of my lower, plus a sulfur plus 2H2O, right? So now I have to cancel out everything that occurs more than one time. So I cancel my 4 electrons, 4H plus on this side, 4H plus on this side, right? And now I combine the things that are on both sides, like 2 sulfurs, and over here there's a third sulfur, so I need to combine them. So now I write a combined proper equation in which everything's cancelled. So my proper equation comes out to be 2H2S plus SO2. It's going to form 2S plus 1S. So 2 sulfurs here plus 1 sulfur here, you form 3 sulfurs. So 3 sulfurs plus 2 times water. So that's my full balanced chemical equation. Now the question says that how many moles of H2S are needed to react with sulfur dioxide to produce 1 mole of sulfur. Okay, so if 2 moles, now I'm going to use the ratios. If 2 moles of hydrogen sulfide react, they form 3 moles of sulfur. So according to my ratios, hydrogen sulfide ratio sulfur, right? Hydrogen sulfide ratio sulfur is 2:3. So if I need to form 1 mole of sulfur, I require X moles of hydrogen sulfide. So the value of X comes out to be 2 times 1 equals to 3 times X. 2 upon 3 equals to the value of X, and 2 upon 3 moles of hydrogen sulfide are going to be required, which makes option B to be the correct answer. Okay. Which statement is correct? The relative atomic mass of a chlorine 35 atom is 35.5. No, that's incorrect. Not the relative atomic mass. The relative atomic mass of just chlorine is 35.5 because the relative atomic mass includes both the isotopes of chlorine. In fact, all the isotopes of chlorine. So this is incorrect. The thing that makes it incorrect is this: the relative atomic mass of just chlorine is 35.5. So there should have been a chlorine here. Next statement. The relative molecular mass of O2 is 16. This is incorrect. Why? The relative molecular mass of O2. So you can see that there is a small 2 written over here. This means that there are two oxygen atoms that are covalently bonded like this. So you have one oxygen, you have another oxygen like this. There's a double bond between them. So that's a oxygen molecule. And the mass for this is going to be the mass of two oxygen atoms added, which is 16 plus 16, which makes it 32. So that's incorrect. The relative formula mass of calcium carbonate is 100.1. So let's calculate the relative formula mass for calcium carbonate. For that, we need the mass of calcium, carbon, and 3 times the mass of oxygen. So we're going to go to the periodic table. For carbon, it's 12.0. For oxygen, calcium, it's 40.1. And for oxygen, it's 16. Okay, first 40.1 for calcium plus 12.0 for carbon plus 3 times 16.0 for so we're going to calculate it out. 40.1 plus 12 plus 16 times 3, which comes out to be 100.1. So equals to 100.1, which makes option C the correct option. The relative isotopic mass of magnesium 24 is 24.3. The problem here is that isotopic mass means the mass of one isotope, and that's the isotope they're talking about. If they're talking about this isotope, the mass of this isotope has to be 24. 24.3 is the relative atomic mass of magnesium. The isotopic mass is the mass of only one isotope, which is 24. The bonding between two atoms of nitrogen in a nitrogen molecule involves the hybridization of atomic orbitals to form sp orbitals. Okay, so we have a nitrogen, and that's triple bond to another nitrogen. And they're saying that the hybridization of this nitrogen and this nitrogen is sp. Okay, formation of sigma bond between the two nitrogen atoms in N2. Okay, an sp orbital from one atom overlaps with an sp orbital of the other atom. An sp orbital from one atom overlaps with an sp orbital of the other atom. An s orbital from one atom overlaps with a p orbital and s orbital. Okay, so what happens is that when your sp hybridized, that means your two atomic orbitals are only hybridized. The remaining two orbitals, okay, so this yellow orbital, it's hybridized. Why? Because this has to form sigma bond, but the pi bonds is basically formed between unhybridized orbitals. So these two green orbitals, these two green bonds, they're going to be pi bonds. So they're going to be formed between unhybridized p orbitals, right? So they're formed between unhybridized p orbitals. Now this sigma bond involves your hybridized orbitals, and the other lone pair that's going to be present here, this and this, okay, it's going to be something like this. So basically that's how a nitrogen atom basically bonds. So only two orbitals are involved in hybridization, right? One s and one p. So an sp orbital from each atom overlaps, yeah, either this or this. Type of orbital which contains the lone pair on the nitrogen atom, it's sp. Why is it sp? You got to realize one thing that's very important, which I was talking about, the lone pair. That's where your chemistry basics come. Okay, now I'm going to draw everything to you so that you guys see. This is one nitrogen, this is the other nitrogen. I know this is going to create confusion, but please listen to me. Now, look, it has 5 electrons. 1, 2, 3, 4, 5. 1, 2. 1, 2. Let's draw it with a cross. 1, 2, 3, 4, 5. Now, you have to form 2 pi bonds, right? Between these 2 electrons and these 2 electrons, pi bond is formed. And pi bonding happens in unhybridized orbitals. So these and these electrons, they're basically unhybridized. They're present in unhybridized p orbitals, right? So they're present in unhybridized p orbitals. Now, where is the sp hybridization, the s orbital and the p orbital? Where are they gonna basically intermix with each other? This is where they do it. This lone pair and this pair, right? Now this is gonna form sp hybridized orbitals. This might be, I'm just randomly taking an example. This might be an s orbital, and this one right here might be a p orbital, right? This one over here might be a p orbital, and this one right here might be an s orbital. No one cares. Now what's gonna happen? This and this, they're gonna bond together, intermix with each other. Hybridization is gonna occur over here, and now what is gonna happen is that you are gonna form two hybridized sp orbitals like this over here, and this is one sp orbital, this is another sp orbital, this is one sp orbital, and this is another sp orbital. Do you get it? That's how hybridization works. Even the lone pairs, they are also present in hybridized orbitals. Okay? So even the lone pairs are present in hybridized orbitals, though they're not involved in bonding. You got to realize this thing. That's how it's happening. So this lone pair is going to be in this sp orbital, and this single pair is going to be in sp, going to make a bond with this, which is also present in sp. That's how the bonding works in nitrogen. So to make sure that you are able to do this, your concepts of bonding should be very strong. Next question. 3 bond angles are labeled on the molecule as shown. What is the order of decreasing size of the bond angles X, Y, and Z? So we have to tell from the largest to the smallest. Let's see. Over here, we can see we have 3 bond pairs, 1 bond pair, 2 bond pair, and 3 bond pairs in a lone pair. So remember, whenever you have 3 bond pairs and a bond pair on the top, right? 4 bond pairs, the angle is 109.5. But now, when this top pair is replaced by a lone pair, something like this, what happens is this 109.5 angle decreases to almost 107.5 or something like this, around 107. So this one is going to be 107. For this is a simple carbon atom that's bonded to 4 other atoms. There are no lone pairs here. So this is going to be 109. This one right here, it might seem like it's a 180 degree, but that's not correct. It's not 180 degree. You can see there are 2 lone pairs. So what's happening over here is this is your sulfur, and these are 2 hydrogens that are bent, and you have 2 lone pairs on top, something like this. Okay, so you got to realize one thing over here. When you have 4 bond pairs, okay, the angle is 109.5. When you have 1 bond pair and 1 lone pair, the angle comes out to be 107. And when you have 2 lone pairs, as the number of lone pairs increases, the angle decreases, the angle reduces to 104. So this angle is going to be approximately 104, right? So the largest is going to be Y, the smallest is going to be X, and in between is going to be Z. So that's how you do it. X and Y are different elements in period 3. So let's list down period 3 elements. We have sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, and argon. Atoms of X and Y each have only one completely filled orbital in their highest occupied energy subshell. Okay, atoms of X and Y each have only one completely filled orbital. So we're talking about a completely filled orbital in their highest occupied energy subshell. So this is your nucleus, and as you move away from the nucleus, what happens is that your energy level increases. So in the highest subshell, basically they have one completely filled orbital. Y has greater first ionization energy than X. Which row shows the structure and bonding in Y and X? If we talk about sodium, okay, the last orbital, which is going to be S because it's an S block element, is going to just have one electron in it, right? If we talk about magnesium, the last is going to be S because it's an S block element. The highest subshell is going to have 2 electrons in it. If we talk about aluminum, since it's a P block element, so the highest energy subshell, which is going to be, now we would have to draw 3 for aluminum, something like this, something like this. This is going to be aluminum, this is going to be silicon, phosphorus, all are P block. This one's for sulfur, this one is for chlorine, and this one is for argon. So these are their P orbitals together that I've drawn. So now aluminum is going to have 1 electron in one of the 3 orbitals, 3 P orbitals. Silicon is going to have 2 electrons like this. Phosphorus is going to have 1, 2, and 3. Sulfur is going to have 1, 2, 3, and then the 4th one right here. Chlorine is going to have 1, 2, 3, 4, and the 5th one here. And argon is going to have 1, 2, 3, 4, 5, 6. And now let's read the statement again. Atoms of X and Y each have one completely filled orbital. Atoms of X and Y each have only one completely filled orbital. So there should only be one completely filled orbital. So now we see that over here there are 2 completely filled orbitals in chlorine, right? This one and this one, so cross. In argon there are 3 completely filled orbitals, cross. In phosphorus there's no completely filled orbital. In silicon there's no completely filled orbital. In aluminum there's no completely filled orbital. So only sulfur has one completely filled orbital, which is the one of the P orbitals, Px you can say Py or Pz, and magnesium has a completely filled orbital because you can see sodium also does not have a completely filled orbital. So the 2 elements we're talking about is magnesium and sulfur. You can see it for yourself. Y has a greater first ionization energy than X. So you should know that across a period, the ionization energy increases. So Y has a greater first ionization energy, so Y is going to be here and X is going to be here. So probably then X got to be magnesium and Y got to be sulfur, because we know sulfur is going to have more ionization energy than magnesium, because sulfur is basically it's more on the right side of the periodic table. So if we talk about magnesium, it has a giant metallic structure, and if we talk about sulfur, it has a simple molecular structure, which makes option B to be the correct one, right? Next, a pure sample of a gas has a density of this at this much pressure and this much of the temperature, the gas behaves ideally under these conditions, which expression gives the MR of the gas. So to calculate out the MR, you got to write the formula first and then you have to manipulate the formula. First, forget about the options. Just write the ideal gas equation, which is PV equals to nRT. Pressure, volume, N R for general gas constant, T for temperature. PV equals to N is the moles, right? So for moles, you can write it as mass over MR times R times T. Now you got to make MR your subject. Why? Because we have to calculate out the MR. So PV comes down here. Now you know one thing, that mass upon volume, you can write it like this as well, times R times T upon your pressure. That's the same thing. Okay? I've just written it in a different way, but that's the same expression that I've written over here. Now this equals to your MR. Mass over volume equals to your density. So you can say that MR equals to your density times R times T upon your pressure. Do you get it? So now what do you have to do? You have to look at your density, but there's a problem with your density. The problem with your density, it's in gram per dm cube, and we have to take it in gram per meter cube, right? Meter negative 3. So what we're going to do is we're going to convert it. So first things first, how do we convert it? First, how do we convert it? We look at the equations, and if I try to match my answer with this to this, first let me just write these values, and then the conversion is going to be a later step, because I might not have to do it if it might happen on the way. So density is 2.62 times R, which is 8.31, times temperature. You have to remember one thing. You have to take the temperature in Kelvin. You cannot take it in degrees Celsius. So temperature has to be in Kelvin. And how do you take 25 degrees Celsius to Kelvin? You add 25 plus 273. So 25 plus 273. 25 plus 273, that gives me 298, times 298 divided by the pressure. Pressure is 101,000. So this equation is wrong. This equation is wrong. This is wrong because the pressure, this temperature is taken in degrees Celsius. We have to take it in Kelvin. This equation is only correct. And the only thing that might disturb you is this value. What is this? This is basically, they're trying to convert your gram per dm cube into gram per meter cube, right? So they're trying to convert it into gram per meter cube. Why? Because for density you have to take it in meter cube, because you take the volume in meter cube, and so they've divided it by 0.000001. So that's why your option D is the correct one, right? Why is that so? Because you should know that 1 meter cube contains 1,000 dm cube. So 2.62 upon 1 dm cube basically means 2.62 upon how many meter cube? Convert this dm cube into meter cube, divided by 1,000. 1, 2, 3, 0.001 meter cube. Get it? That's why it's T. When 0.47 gram of a hydrocarbon is completely burnt in air, the energy released heats 200 gram of water from this to this, what is the amount of energy absorbed in joules by the water? So first we have a very basic formula that we use. It's Q equals to mc delta T. For Q, it's basically the energy, which we don't have. M is the mass of the hydrocarbon that we're using, which is 0.47. C is basically your that's the specific heat capacity of water, which is 4.18 times change in temperature. I've done one mistake over here, and you guys got to realize the mistake. If you guys realize the mistake, that means that you're going well. I've done a mistake, and I'm going to tell you at the end what mistake am I making. Okay, and then we have to take the change in temperature. You can take the change in degrees Celsius, because you take the change in degrees Celsius or Kelvin, the change does not change, right? So it's 41 minus 23.7. So now, the mistake that I was making, it was this mistake, 0.47. Always remember, to calculate out the energy that's absorbed by water, we have to take the mass of the water. Mass of water is important. So this is the mass of the hydrocarbon. We have to take the mass of water, which is 200 grams. So that's incorrect. So it's 200 times 4.18 times 41 minus 23.7. So let's check what we get. 41 minus 23.7. 41 minus 23.7 and 17.3 times 17.3. So which makes option number C the correct one. 200 times 4.18 times 17.3. 200 times 4.18 times 17.3. One commercially available heat pad contains iron, activated carbon, and water. The heat pad is activated by air. This causes the pad to get hotter. Which statement describes the chemical reaction occurring in the heat pad when it is exposed to air? So firstly, you got to realize that what's happening in that thing is that you have iron in it, you have carbon in it, activated carbon, and water. And it's activated by air. Air contains oxygen, you know it. And this causes that thing to get hot. So that means, what kind of reaction is occurring which is making it hot? There must be an exothermic reaction occurring, right? Because it's getting hotter. So you can straight away cut off the options which say endothermic. The reaction is exothermic and iron gains electrons. The reaction is exothermic and iron loses electrons. Now, does iron gain electron or iron lose electrons? We got to realize it. Can iron gain electron? What do you guys think? Iron is a metal. Okay? And you should know that metals form positive ions. Iron can only form, like normally when it's going to react with natural things, it can either form iron 3 plus or an iron 2 plus ion, right? That's how iron reacts. So iron only loses electrons because it's a metal. Metal gaining electrons is not possible unless we forcefully do it. By nature, the reaction is not supported by nature, in which a metal can, basically gain electrons. So it's going to be option number D. In which substance is the average oxidation number of sulfur the highest? Let's calculate it out. In the first one, it's 0. You can see it's a free element. Sulfur bonding with sulfur is going to have an oxidation number of 0. Over here, for sodium, it's a positive 2 in total. For one sodium, it's a positive 1. For oxygen, in total, it's negative 2 times 6, which is negative 12. One oxygen is this. To balance out a negative 12, you need a positive 12. You already have a positive 2, so you'd need a positive 10. And now, this positive 10 is being given by 4 sulfurs. So 1 sulfur is going to give positive 10 divided by 4. Positive 10 divided by 4, which gives 2.5. So over here, sulfur has a charge of 2.5, average charge, right? Over here, positive 2 for 2 sodiums, negative 6 for 3 oxygens. To balance out a negative 6, you need a positive 6. So a positive 6 out of positive 6, you already have a positive 2. So now you just need a positive 4 and positive 4 given by 2 sulfurs. So for 1 sulfur, it's going to be a positive 4 divided by 2, which is a 2 average charge. For here, oxygen is definitely going to be electronegative. So it's going to be a negative 4 for oxygen. To balance out a negative 4, what do we need? To balance out a negative 4, we basically need a positive 4. Now we have chlorines and we have sulfur. So if we take chlorine as a negative 1, there's going to be a total of negative 6 charge. And then sulfur could lose all its 6 electrons and give us a positive 6 charge. So done. The highest oxidation number is in option number D, positive 6. Over here it's a 2, it's a 2.5, over here it's a 0. So positive 6 over here. Because 1 chlorine is negative 1. 2 chlorines are going to be negative 2. Negative 2 plus positive negative 4. Negative 6. To balance out negative 6, we need a positive 6. And sulfur can give a highest oxidation number of positive 6, because you should remember that in the last shell of a sulfur atom, something like this, you have 1, 2, 3, 4, 5, 6 electrons. So basically, sulfur can oxidize to lose all of its 6 electrons. Something like this. An equilibrium can be represented by the equation shown. This is the equation. In a certain mixture of volume 1 dm cube, the equilibrium concentration Q is 10 mole per dm cube. Okay. In a volume of 1 dm cube, the equilibrium concentration of Q is 10 mole per dm cube. What will be the new equilibrium constant of Q if 5 mole of pure Q is completely dissolved in the mixture? Okay, so what's happening is that we have P, we're making it react with Q, and then we're forming 2R and S. The equilibrium concentration of Q is 10 mole per dm cube. At equilibrium, we have 10 mole per dm cube of Q. What will be the new concentration of Q if 5 mole of pure Q is completely dissolved in the mixture? So we're adding Q. When we're going to increase Q, what's going to happen? The equilibrium is going to move forwards, right? So, and it will try to balance out everything that we do. So we try to increase the concentration, the equilibrium is going to try to decrease it. So since equilibrium will try to decrease it, it cannot be 15, yeah? We're sure about it. It cannot be between 5 and 10. Why would it drop like below the original one? No. So now there are two options, between 10 and 15 and 10 mole per dm cube. Now you got to realize one thing. Equilibrium is slowly trying to decrease it. So it cannot reach exactly back to 10. So it's going to be somewhere between 10 and 15, right? This was a tricky question that required a little bit of logic to be used. And this was indeed a challenging question. So if you're unable to solve it, don't worry. You just got to realize that equilibrium is trying to decrease it, right? So that's why it's going to be somewhere between this and this, because it's decreasing. In the contact process, sulfur dioxide and oxygen react to form sulfur trioxide. In the Haber process, nitrogen and hydrogen react to form ammonia. Which statement about the processes is correct? Kp for the Haber process has no unit. We got to figure it out. Kp for the Haber process. For the Haber process, I have my hydrogen, I have my nitrogen, and I form 2NH3, and then I have a 3 here, and that's Kp has no units. So Kp is gonna have products over reactants. So the concentration of the products times, it's gonna be a square above. Then for hydrogen, it's gonna be a cube times nitrogen, it's gonna be a raised to power 1. So above it's 2 and below it's 3 times 1. So basically it's the above and below, they're not equal, so they're not gonna exactly cancel out. It's gonna have some units, right? Because there's a 3 and 1 here, right? So it's gonna have some units. It's not gonna cancel out. So this one is incorrect. In the contact process, the value of Kp falls when the pressure is increased at a constant temperature. So you have sulfur dioxide, you're trying to add oxygen to it to form sulfur trioxide. And now, since the equation is not balanced, you added 2 here, then you added 2 here. Now see if it's balanced. Yeah, it's balanced now. So the value of Kp falls when the pressure is increased. So if you increase the pressure, what's going to happen is that, when you increase the pressure, the equilibrium move towards the side that has less moles. So equilibrium is going to move forward. So if equilibrium move forward, that means that more product is going to be formed. And if more product is going to be formed, the Kp expression is the concentration of your products over reactants. So Kp basically has a direct relation with products. So if products is going to increase, Kp is also going to increase. So this is incorrect. The Haber process uses a homogeneous catalyst. No, it uses a heterogeneous catalyst. Why? Because in the Haber process, you use a piece of iron as your catalyst, Fe, right? This is your Fe, which is iron. And all the reactants, which is nitrogen and hydrogen, are gas. When your reactants and your catalyst are in different states, right? That's a heterogeneous catalysis. So instead of being homogeneous, it's going to be a heterogeneous catalyst, because catalyst is solid and your nitrogen and hydrogen are gases. So this is also incorrect. When V2O5, which is the vanadium oxide, which is a catalyst for the contact process, the position of the equilibrium is unchanged. That's 100% correct, because a catalyst does not affect the position of the equilibrium. So when you're going to add this catalyst, your equilibrium position is going to remain unchanged despite the rate increasing. 20 cm cube of hydrogen peroxide decomposes to water and oxygen in the presence of a suitable catalyst. 160 cm cube of oxygen measured at room condition is produced in 5 minutes. What's the average rate of decomposition of hydrogen peroxide during this reaction? So let's write the equation. In chemistry, when you do chemistry for a long time, then before doing anything, you are just like, I want to write the equation so I know what's happening. H2O2 is forming water plus oxygen, I guess, since the equation is not balanced. So we're going to add a 2 here and a 2 here, and then we would have to add a 2 here too, right? Now it's balanced. We have 4, we have 4, we have 4, 5, 6, so we would have to add a. So we are forming water and oxygen, so we would have to add a. So to balance it out, we can simply do is that can write half here, right? So I guess that's the way we could have done it. Balanced. Okay. Now 20 cm cube of H2O2 decomposes. So we have 20 cm cube of this that's being decomposed. What in the presence of a suitable catalyst? 160 cm cube of oxygen is present. Okay. 160 cm cube is made in 5 minutes. We are now dealing with what's the average rate of decomposition of hydrogen peroxide. So rate equals to, now it's given in moles per second, equals to change in moles or concentration, whatever, divided by the time. We know time is going to be 5 minutes, so it's basically going to be 5 times 60 because we have to take it in seconds. But the change, initially you should know that you have 0 cm cube of oxygen, right? And now you have 160 cm cube of oxygen. You should remember one thing, that you can calculate out the moles of oxygen. Initially you had 0 moles, and now because you had no oxygen, now you have 160 cm cube, right? So it's gonna be moles equals to your volume, which is 160, divided by 24,000. 160 divided by 24,000, 0.00667. So we have 0.00667 moles. Okay, 0.00667 moles divided by 5 times 60, it's gonna give me 300, I guess, divided by 300. One, two, three, four, 5. 2.2 into 10 raised to power negative 5. So if 2.22 into 10 raised to power negative 5 moles per second is changing, this much amount of oxygen is being formed per second. This much moles of oxygen is being formed. Now look at the molar ratio. This much moles of oxygen is being formed every second. The molar ratio is, for oxygen and hydrogen peroxide, it is basically change in reactants, right? The change in the moles of your reactants. So the ratio for oxygen and hydrogen peroxide is basically 1:1/2, or you can say 1:2. So if I remove this half, because I know it's confusing for you, multiply both sides by 2, this by 2 and this by 2, right? So what do we get? We are first going to remove this half because I know it's confusing you, so it's going to become 2:1. So this is 2:1. So hydrogen peroxide is basically double. Double the moles of hydrogen peroxide are being used compared to what oxygen's moles are being formed. So if this much mole of oxygen is being formed every second, then the double of this much moles of hydrogen peroxide is being used up every second. So we have to look at the change in the rate of, they're asking for the average rate of decomposition of hydrogen peroxide during this reaction, not of oxygen, of hydrogen peroxide. So these are the moles of oxygen that we calculated, that were changing every second. But we have to calculate for hydrogen peroxide. For hydrogen peroxide, it's going to be double because of this 1:2. That's why I say you got to write equations. So if we double it, we are going to get this, because 2.22 multiplied by 2 is going to give 4.44. And that's just because we wrote the equation. Which reaction pathway diagram shows an endothermic reaction that occurs in 2 steps, and in which the second step of the reaction is likely to be faster than the first? So firstly, we have to see that the second step is likely to be faster than the first. Which reactions are faster? Those reactions are faster that have a lower activation energy. So the second step should have a lower activation energy than the first. Over here you can see the second has a higher. So cross. either this or this. Now, what kind of reaction are we looking for? Endothermic. So, products should have more energy than the reactants. So, over here, let's see. These are your reactants, these are your products, these are your reactants, these are your products. Products should have more energy than the reactants. Over here, you can see that your reactants have more energy, products have less energy. Over here, reactants have less, products have more. So we need the one in which products have more energy, which makes option C the correct one. Oxides of nitrogen are involved in the formation of photochemical smog and acid rain. Which oxides of nitrogen are involved in each of these processes? So for photochemical smog, I guess it's going to be A. All oxides are going to contribute equally. There is no specific oxide because nitrogen monoxide can also form nitrous acid and nitrogen dioxide can also form. And for photochemical smog, both oxides can react. So for me, it's going to be A. Like, they're oxides. And this oxide, by the way, can easily oxidize into this oxide. And this oxide can easily reduce into this oxide. So they're interchangeable kind of things. Sodium and sulfur react together to form sodium sulfide. How do the atomic radii and the ionic radius of sodium compare with those of sulfur? So you know that what happens across the period? Across the period, your atomic radius decreases. So this is sodium, this is sulfur. So the atomic radius, sulfur, sodium is going to have greater. Why? Because across the period, you should know that that's a common thing. Atomic radius decreases. But what happens to the ionic radius? Now you got to realize that a sodium ion is a positive one and it has 10 electrons. Why? Because initially sodium has 11 electrons, it loses the last electron and now it has 10 electrons. For sulfur, a S2 negative ion has 18 electrons because initially it had 6 electrons in its last shell and it gained 2, so now it has 18 electrons. So when you draw a sodium ion, you just draw 2 shells. But when you draw a sulfide ion, you draw 3 shells. So obviously a sulfide ion is going to be greater than a sodium ion. So for ionic radius, sulfur is going to have more, which makes option D the correct one. Compound X is an oxide of period 3 element. Compound X is an oxide of period 3 element. Compound X is a white solid at 25 degrees Celsius. This means not a liquid, not a gas. So if we talk about, we have sodium oxide, we have magnesium oxide, we have aluminum oxide, then we have silicon oxide, then we have phosphorus oxide, P4O10, then we have sulfur dioxide. That's all what we know. It reacts with water to form an acidic solution. What is compound X? So firstly, we know one thing for sure. Sodium oxide is going to form alkaline solution. Magnesium oxide is going to form alkaline solution. Second thing that we know, silicon dioxide is not going to react with water, right? We know this. So silicon oxide is not going to react with water. And then we know that our very own aluminum oxide also does not react with water. It only reacts with acids and bases. So, and sulfur dioxide is not a solid. It's gas. So the only oxide left is P4O10, which I would have to select, which makes option D the correct option. So you just got to realize that this guy and this guy, they don't react with water. Their chlorides do react with water. They hydrolyze in water, but their oxides don't react with water. This guy and this guy, they form alkaline oxide or basic oxides. And this guy's oxide is not a white solid at 25. You know sulfur dioxide is a gas. So the only guy left is P4O10, which is a solid as well as going to form phosphoric acid once in water. When heated, magnesium nitrate decomposes. Which equation for the thermal decomposition of magnesium nitrate is correct? So, I've learned the equation. I am a hardworking person, so I've learned it. Not this, not this, not this. It's option C. Because you form nitrogen dioxide. I've learned it. I'd be honest. I've just learned it, learned the equation from the book because it was used so many times that I had to learn it. So now it's on my fingertips. R is an aqueous solution of an ionic compound. A white precipitate is formed when R is added to strontium nitrate. Okay. So we know that R must contain strontium. So strontium sulfate, SO4, is gonna be insoluble. That is what I am thinking. Okay? So it might contain sulfate or might contain, this is what I think, that's how my mind operates. So R might contain a sulfate. I've not done these questions before. I'm doing them for the first time, I'll be honest. And that's how I think. No visible reaction is seen when R is added to dilute HNO3. So that means strontium nitrate might form. NO3 too, which is soluble because all nitrates are soluble, which anion could be present in compound R. I firstly suspected it to be a sulfate ion. Why a sulfate ion? Because of this insolubility. Because you know that down the group for group 2, it's something like magnesium, calcium, strontium, barium. The solubility of the sulfates decreases. So strontium sulfate is definitely going to be insoluble. That's why it's going to form a precipitate. Next, in an experiment, 0.600 mole of chlorine gas is reacted with an excess of hot aqueous sodium hydroxide. One of the products is NaClO3. What mass of NaClO3 is formed? Got to write the equation, got to figure it out. So I have my chlorine gas, I have my NaOH, gonna form 5 NaCl, gonna form 3, I've learned this equation, NaClO3 plus what is gonna be formed. Am I balanced? That's the question. 2 sodiums, 5, I have 6, so I add a 6 here. Now am I balanced? I added 3 here. Am I balanced? I think I'm balanced now. Okay. Is reacted with an excess of hot aqueous sodium hydroxide. One of the products is NaClO3. What mass of NaClO3 is formed? So I know that the stoichiometric ratio between chlorine and NaClO3 is 3:1. So I say chlorine ratio NaClO3 is basically my 3:1. So if I have 0.600 moles of chlorine, I'm going to have X moles of NaClO. And the value of X is 0.600 divided by 3, which comes out to be 0.200. Now I have these many moles. How do I figure out the mass? Mass equals to my moles times my MR or AR. Moles are 0.200 times MR or AR. I just have to calculate the MR of this thing, NaClO3. So sodium is 23, chlorine is 35.5, O3, 16 plus 16 plus 16. I have the MR. I multiply it with the moles, which is 0.200. I get 21.3. So this one right here, option A, is 21.3. So that's what I'm going to form. X and Y are sodium salts of group 17 elements. When X reacts with concentrated sulfuric acid, H2S is produced. So you should know this reaction by heart. What are they talking about here? They're talking about what kind of element. They're talking about iodine here, because only iodine, when react with iodide ion, which is going to be present in the sodium salt, is going to react to form H2S, because that's a good reducing agent. This iodide ion is a good reducing agent. So I'm going to write X is definitely iodide, because iodide ions are good reducing agents, whatever. When Y reacts with concentrated sulfuric acid, there's no change in the oxidation number of sulfur, why is definitely going to be chlorine? Because you know that chlorine is the chloride ion. It's going to be a chloride ion because we're dealing with salts, sodium salts. So it's going to be a chloride ion. Why? Because we know that chloride ion is worst reducing agent. So it can basically not reduce sulfur. It cannot make sulfur gain electrons. So sulfur has the highest oxidation number. Why? Because it cannot gain electrons, cannot get oxidized. So aqueous X, which was our sodium iodide, and Y, which is our sodium chloride. Now let's read the options. Aqueous X reduces aqueous bromine. So aqueous X reduces bromine. Reduces means makes it gain electron. Yeah, that's correct. If you have iodide ion, it's going to reduce bromine. That means it's going to make bromine gain electron because iodine is lower in the reactivity series compared to bromine. So this option seems correct. I'm not going to read the other options because I am dead sure about this. Okay. Element E is in period 3. It forms a chloride which reacts with small amount of water to produce a white precipitate and steamy fumes. The precipitate is soluble in NaOH and HCl. If we deal with silicon, definitely the precipitate it's going to be SiO2, which is insoluble. If we deal with magnesium, we cannot form MgCl2. Basically, it does not form an acidic solution. Now we have aluminum and phosphorus. Out of these two, we have to look at the reactions carefully and decide. So for phosphorus, what kind of precipitate are we expecting? For aluminum, we know we form complexes, right? And then we form a H positive ion. And so over here for phosphorus, we know that when you're going to make, if you have a chloride, which is going to be PCl5, make it react with water, we're going to form H3PO4 plus 5HCl, and then we're going to add a 4 here, right? So basically they've said that the precipitate is soluble in NaOH and in HCl. So this precipitate that's going to be formed, it should be soluble. Firstly, we're not forming a precipitate here. So there's no precipitate here. So this is incorrect. We're going to form a precipitate here only, right? And the precipitate is basically going to be an aluminum complex, which is AlH2O5, because one water ion is basically lost its one proton. This aluminum got hold of 6 water molecules. Out of those 6, 5 got attached to it and 1 lost its proton, and the OH is of that one water is here. So that's how you get it, right? And this is soluble. Why? Because it's charged, and charged things are soluble. 4 reaction mixtures are listed. Which reaction mixture produce ammonia as a product? So how do we form ammonia? One of the very basic reaction is that you have a ammonium salt, and you make that ammonium salt react with a base. So let's start with the first one. This is an ammonium salt, that's a base. So this one qualifies. This one's ammonium chloride and barium hydroxide. So ammonium chloride, ammonium can donate protons. It's a proton donor. So when it's going to donate its proton, yeah, you can form barium chloride plus ammonia plus water. So 2 also qualifies. Ammonium chloride plus sodium oxide. Yeah, ammonia can basically donate its proton, right? This is a base. Ammonium ion is an acid, is a proton donor. You can form sodium chloride plus ammonia plus water or whatever. So this also qualifies. Ammonium phosphate plus HCl. Basically both are proton donors. HCl also donate protons and ammonia might also donate protons. So this reaction is not going to happen because you have both acids, right? So 1, 2, and 3, which is option number A for 24. So all these three reactions are going to occur, right? Two statements about molecule of methanol. Methanol is going to be C double bond O. There's going to be an H here and H here. That's what methanol is. It's planar, yeah. The bond angle is going to be 120 degrees because carbon is sp2 hybridized. It contains 3 sigma bonds. Let's see, this is a sigma bond, this one's a sigma, this one's a sigma. So we have 3 sigma bonds. Which statements are correct? Both 1 and 2 are correct. As you can see it for yourself, it's sp2 hybridized and it has 3 sigma bonds. The structure of disodium chromoglycate is shown. This is disodium chromoglycate. How many chiral centers are there in this molecule? So we gotta figure out chiral centers. Okay, I'll have to look at it carefully and then I'm gonna speak anything. This carbon seems like a chiral center. This one right here, if you guys agree, look, it has 4 different groups, one H, one OH, one this thing, and one this thing attached to it. So one chiral center, and then we have you only have one chiral center in it. Only one. Oh, we don't have any chiral centers because I just realized. Look at this part of the chain. Look at this part of the chain. Okay. And now look at this part of the chain. They're exactly identical. And since they're exactly identical, this means this group and this group is the same. So we technically have only 3 different groups, OH, H, and this. So there are going to be 0 chiral centers over here. No chiral center. Because not 3 different groups attached. Not 3 different groups attached. For chiral center, we need 3 different groups. What is the major products when 2-methylpentene reacts with HBr? So we have 1, 2, 3, 4, 5. 2-methylpentene like this. This is gonna react with HBr. This is partial positive, this is partial negative. The negative part is going to go with a carbon that has less hydrogen. This carbon has less hydrogens because it has one CH3 attached to it and no hydrogen. This has 1 hydrogen. So this Br is going to move here and this H is going to move here. So our Br is going to move here, our H is going to move here, and this double bond is probably going to break like this. And now what product we have formed? We have formed 2-bromo 2-methyl 1, 2, 3, 4, 5 pentane. 2-bromo 2-methyl pentane, right? Pen-2-ene is reacted with cold dilute acidified manganate ions. What is the major product? So pen-2-ene. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5 pen-2-ene like this. It's make to react with cold dilute acidified manganate ions. When we make it react with cold dilute acidified manganate ions, it is basically oxidized to an alcohol. And what happens is that this double bond probably gonna break from here and we're gonna form a diol, right? So we're gonna attach a OH over here and another OH over here. So we're going to form 2,3-diol. 1, 2, 3, 4, 5. So pent 2,3-diol, right? A mixture of this and this. No, two products, just one product. So this one I guess matches my option, right? Because this is the CH3 part, and then that's the OHCH, and then we continue with that. So now limonin is shown. Limonin is an oil formed in the peel of citrus fruits. Okay, so this is an oil. What product is formed when an excess of Br2 reacts with limonin at room temperature in the dark? So there's not gonna be no free radical substitution. They're talking only about neutrophilic, electrophilic addition. So firstly, this bond is gonna break, right? And again, a Br is gonna be attached over here, and then a Br is gonna be attached over here. This bond is gonna break, a Br is gonna attach here, and a Br is gonna attach here. So we break the bonds, and when we are gonna break the bonds, we just erase them like this. So we're gonna break this bond as well. Done. So this bond should also break, right? Shouldn't this break? So why is this still here? Cross. Why is this bond still here? Shouldn't this bond probably break? Because we have added bromine into it. So why? So it's gonna be D. Both double bonds broken. Which reaction mixture produces a nitrile? Halogenoalkane with casein and ethanol. This is okay, nitrile, which is C triple bond N. Halogenoalkane with NH3 and ethanol, that's gonna produce an amine, not a nitrile. Ketone with 2,4-DNPH, not a nitrile at all. Carboxylic with NH3 in water. No, it's option A. You have a halogenalkane, you add casein to it, and that's one of the reactions which you guys have studied. So you should not be shocked when, if it's difficult, because that's what you guys have studied. You add casein to halogenalkane. Which reaction is classified as SN1? So basically, when you have a tertiary halogenoalkane, and you add OH to it, like something that's going to contain an OH, or potassium hydroxide or sodium hydroxide. A reaction of 1-chloropropane, no. A reaction of 1-chloropropane, no. We gotta need a tertiary halogenoalkane. A reaction of 2-chloro-2-methylpropane, yeah, with potassium cyanide, not with potassium cyanide, with something that has OH, like potassium hydroxide and ethanol, which makes option D correct. Which reaction mixture produces a primary alcohol as a major product? Propane on with NaBH4. That's a ketone, and the reduction of ketone produces secondary alcohols, not primary. Propene with steam in the presence of H3PO4. Okay, so we have propene with steam, and then we have butanoic acid with LiAlH4. You gotta realize one thing over here, that this reaction, it may be propanine, like 1, 2, and 3. It cannot be propanine or proptuine, right? It always have to be something like it cannot be propanine or tuine. But you realize one thing. Look at it. If, for instance, the double bond is here, one hydrogen. Okay, when your OH and H, this thing is going to be added to your propene, do you realize this OH is going to be partial negative, this H is going to be partial positive, and your negative part goes towards the carbon that has less hydrogen. So it's going to basically attach to this carbon. OH is going to come here, H is going to come here, and this double bond is going to break. So now the major product is going to be propane. Realize it for yourself. It's going to be propane 2-ol. Look at it. This is propan 2-ol. So not propan 1-ol. So not a primary alcohol. It's going to be butanoic acid with LiAlH4. That's going to form butan 1-ol. And one other important thing about acids is they cannot be reduced by NaBH4. So if you use NaBH4, your acids cannot be reduced. Only LiAlH4 can reduce them. Ethene with hot concentrated acidified KMNO4. Ethene. Okay, so carbon double bonded to carbon. Then you have an H over here, an H here, an H here, an H here. Basically, since the double bonded carbon has both hydrogens, it's not going to form acid. It's going to either form carbon dioxide or water. So that's how we do it. Now this thing is heated under reflux with an excess of acidified K2Cr2O7 until there is no further reaction. What is the final product? So let's draw it. H, then there's an OH. Then there's an C double bond O and H. So we are oxidizing it. When we oxidize it, you see this part is going to be oxidized and this part is going to be oxidized. So this part is going to be converted into an alcohol. So there's going to be an OH here. And this part is also going to be converted into an alcohol. So there's going to be a C double bond O, and then there's going to be an OH formed here. And this OH is going to be, this H is going to be removed from here, right? So we're going to form a diethanoic acid. So C, yeah, this seems to be correct. So C is the answer. The question here states that the structure of naturally occurring compound Q is shown. This is compound Q. Compound Q is heated under reflux with an excess of acidified KMNO4. Organic product R is formed. Which row is correct? Okay. So look at the functional groups in Q that are gonna, be heated under reflux with acidified KMNO4 that are gonna be oxidized. Acidified KMNO4, so they're gonna be, we're dealing with oxidation here, right? So what's gonna be oxidized? We can see this one right here, this group, this fella, this seems like a ketone. This seems like an alcohol. Alcohols can get oxidized. This one right here seems like an aldehyde. This one right here seems like a ketone, and this one right here seems like an alcohol. So these are all the groups that have the potential to get oxidized. Organic product R is formed. Results of tests with compound Q. Okay. Orange precipitate with 2,4-DNPH, no reaction with alkaline I2. Okay, orange precipitate with 2,4-DNPH. Yeah, we have aldehydes and we have ketones right here. So yeah, we're gonna get an orange 2,4-DNPH, we're gonna get an orange precipitate. Yeah, and we're gonna get no reaction with alkaline I2, because to get a reaction with alkaline I2, you gotta have one thing, CH3, something like this, and then a C double bonded to O, right? So I don't think we have this kind of thing anywhere. So this one's correct. Red precipitate with Felling's reagent and no reaction with alkaline I2. Might be because we have a aldehyde, I guess. Yeah, this one's right here. This one's an aldehyde, right? So yeah. Yellow precipitate with alkaline I2. No, we're not expecting yellow precipitate. Results of test with organic product are yellow precipitate with alkaline I2 and no reaction with Felling's reagent. Orange precipitate with 2,4-DNPH and no reaction with alkaline I2. Ketones cannot, you gotta realize, ketones basically cannot get oxidized. So this ketone cannot get oxidized, this ketone cannot get oxidized, and this aldehyde is gonna get oxidized. 2-carboxylic acid. This aldehyde is gonna get oxidized to carboxylic acid. So yellow precipitate and no reaction with Felling's reagent. Yeah, that's correct. Yellow precipitate with alkaline I2. No, you're not gonna get a yellow precipitate because you basically cannot form this thing. No, that's incorrect. So this one's correct. that you're going to have orange precipitate with 2,4-D and pH because your ketones are going to be there, and no reaction with alkaline I2 because you cannot form this thing. This thing is what you need, which you don't have in here. You can check it out. Which organic starting material could be used in a single reaction to produce propanoic acid? In a single reaction to produce propanoic acid, so we have ethane nitrile. I don't think propane 2-ol. Propane 2-ol will form a ketone. Yeah, why a ketone? Because it's gonna form a ketone, propane 2, because it's a secondary alcohol, and secondary alcohols are oxidized to ketones, not to carboxylic acid. Propanol, yeah, that's correct. Propanol is going to be oxidized to a carboxylic acid. Propyl ethanoate. Ethanoate is basically the acid part, so it's going to form ethanoic acid, which makes option C to be the correct one. So now we have in 4 separate reactions W, X, Y, and Z, 1 mole of an organic compound reacts with an excess of a reagent. So we have sodium, we have sodium carbonate, we have sodium hydroxide, and we have another sodium. And 1 mole of organic compound will react with excess of the reagent that we're basically using here. So you got to realize one thing, that what's happening is the volume of any gas produced is collected and measured. All gas volumes are measured at the same temperature and pressure. What is the order of the reactions from greatest total volume of gas collected to the least total volume? Okay, this is going to be interesting. So over here, I would have to look at the functional groups. I have one OH, I have one carboxylic, and another carboxylic. Over here, I know I'm not going to produce any gas. NaOH, no gas, right? So least is going to be with Y, right? And the most is going to be with, let's check out, sodium carbonate. COH acid, yeah. OH, nah. And this thing has 2 COH groups. So you should realize the greatest is gonna be with Z. Why with Z? Because it has 1, 2, 3 groups that are gonna react with Na. This thing has only 2 groups, right? And now since this thing also has 2 groups and this thing also has 2 groups, I think that now we gotta do something and realize about that. When we have an acid and we make it react to form carbon dioxide or hydrogen, this OH is not going to react with sodium carbonate, right? Over here, both COH are going to react with sodium. So W definitely is going to produce more gas because both COH are going to react. Took a little bit of time, but I got. Butyl amine can be produced by the reaction of butane nitrile with hydrogen in the presence of a suitable catalyst. Which volume of hydrogen measured at room conditions is required to react completely with 0.5 gram of butane nitrile? So first let's draw butane nitrile. 1, 2, 3, and 4. And the 4th carbon is going to be triple bonded to an N. Right? Now this is butane nitrile. Over here, there is going to be H, 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 H. And this is how butane nitrile is going to look like. And when you're going to add hydrogen to it, H2, what's going to happen? One bond is going to form here with H, one going to form here with H, and these 2 bonds are going to get broken from the middle. The pi bonds are going to get broken, and then 2 bonds are going to form here. So in total, how many moles of hydrogen are you using? You're using 2 moles of hydrogen. This is 1 mole of hydrogen, H2, and this is the other mole of hydrogen, H2, to basically convert this butane nitrile to butylamine. So ratio between our butane nitrile and hydrogen is 1:2. So if we have 0.5 gram of butane nitrile, 0.5 gram, how many moles do we have in 0.5 gram? 0.5 divided by the MR. MR is 70. Calculated for butane nitrile, it's going to be 70. 0.5 divided by 70. Let's check. It gives me this much of my MR, right? Of my moles. So these are my moles. Now, if I get this moles, if 1 mole gives me this, then these many moles will give me X moles of hydrogen. X comes out if I multiply my answer, which I just got, by 2. So I'm going to multiply my answer by 2. Now, these are my moles. Now, I need the volume, right? I need the volume of hydrogen. So I'm going to multiply my moles by 24,000. I'm going to get the volume, which is 342.8. 342.8, which is closest to option number D, right? Almost 343 it comes out to be. I guess there's a small error or something. 1, 2, 3 bonds here, 2 bonds here. Still, I guess D is the correct answer. So we're close to it, but there's something up down here, right? I guess with the MR we have done something up down, yeah? MR might not be correct, so let's do the MR again. 1, 2, 3, 4, 5, 6, 7, 1, 7, and then 1, 2, 3, 4, 5, 6, 7. So I guess my MR has some issue. 12 times 4 plus 14 plus 7 times 69. I don't know. There's a little issue, but it's rounding off to this. A section of an addition polymer is shown. Which monomer is used to make this polymer? Step 1. Identifying the repeat units. Yeah, that's going to be our step 1. We identify the repeat unit. I guess this is the repeat unit, yeah? I'm just guessing it. Yeah, you look at it and then you guess it. If I break it from here and then I break it from here and then I break it from here. So this thing is my repeat unit. If I draw my repeat unit, it is carbon. It has 1, 2, 3, 4 carbons. So 4 carbons in my 1, 2, 3, 4 carbons. Yeah, I have 4 carbons. And there is one other thing. 1, 2, 3, 4. 1, 2, 3, 4, 5. Not 5, I have 4 carbons. 1, 2, 3, 4 carbons. I should have 1, 2, 3, 4, 5. No. So you got to be careful with what you're doing. So I should have. So I crossed this on the basis of carbons. Now between A and B I need to decide. So now I need to look at the structures. Carbon double bonded to O and then a CH3. Carbon double bonded to O, then a CH3. Carbon double bonded to O, and then I need a CH3 methyl group over here. Over here I have this methyl group, but over here I don't. So option A is going to be the correct one. Do you get how did I just solve it? Just a little hint I need, and I'm going to get to the correct answer. That's how I work. First I counted the carbons. In C and D the carbons weren't enough. Then I just looked that the double bonded carbon has a methyl attached to it. Over here the double bonded carbon had no methyl, but over here the double bonded carbon had methyl. So option A became my correct answer. Okay. The purity of a compound can be determined by using infrared spectroscopy. The table gives the characteristic of infrared absorption frequencies of some selected bonds. So that's for hydroxyl, aromatic alkane, amide, carbonyl, carboxyl ester, and everything. Propanol is made by the hydration of propene. A sample of the product is obtained. Which feature of the infrared spectrum of the product would show that no propene remains in the product? So no propene. So we know that if no propene is going to be in the sample, then we're not going to have any alkene absorption. So this one, aromatic compound or alkene, which is this, is going to be absent in the sample. So it's going to be lack of absorption at this point, which tells about the alkene, right? So over here we are done with our paper.